Good afternoon, everyone. This is Ramireddy, Assistant Professor in Chemistry, Department of Basic Sciences and Humanities. Today, the course name is Pharmaceutical Chemistry. The topic is Optical Isomerism. So we are going to discuss about what is the optical isomerism, and we will discuss two examples to explain the optical isomerism concept. So here, optical isomerism. Optical isomers. What are optical isomers? The optical isomers are stereomers. The optical isomers are stereomers. What are the stereomers? The stereomers are the isomers with same molecular formula. Same molecular formula and different arrangement of atoms. Different arrangement of atoms or groups are called as stereoisomers. Optical isomers comes under the stereoisomers, a class of stereoisomers. What are the stereoisomers? The stereoisomers are the isomers with same molecular formula but different in the arrangement of atoms or groups. We will try to explain with one example. What are the stereomers? I will take one example. Right, see. Here we have two compounds. Here we have two compounds. In the first compound, the molecular formula of the first compound is C2Cl2HBr. C2Cl2HBr. Coming to the second compound, the molecular formula is again C2Cl2HBr. Means both are isomers. Both are having the same chemical formula or molecular formula. But what is the different? We already said that, discussed that stereoisomers with same molecular formula but different in the arrangement of atoms. In the first structure, see here the arrangement of atoms. The chlorine on the first carbon and the chlorine on the second carbon. Both the chlorines are same side of the carbon-carbon double bond in the compound 1. Coming to the second one, the chlorine atoms. The chlorine atoms are opposite sides of a double bond. So, such type of isomers are called as the stereomers. That is the definition of the stereomers. Next, what are optical isomers? Optical isomers. Right, now that will be the same molecular formula, but the isomers which rotate plane polarized light. The isomers which rotate plane polarized light, PPL. Such type of compounds are called as the optical isomers. Right? Before entering into in detail, first we have to know about the plane polarized light. What is the plane polarized light? Right. Coming to that, first generally we know that ordinary light. Right. This is the ordinary light. The waves of the ordinary light oscillates in infinite number of directions. Here I am writing C. Let's say this is some system in a room. If you switch on the light, let's say you are at the center of the room, the directions of the waves of the ordinary light oscillates in at infinity number of directions. Here we have infinity number of directions. But these infinity number of directions are then passing through a polarizer, or Nicol prism. Now this ordinary light beam, which oscillates in infinity number of directions, is passing through a polarizer or the Nicol prism. Then the infinite number of directions are now vibrate in a single plane. Again the same room. Now it is a single plane. Such type of the light is called as plane polarized light. We will discuss one more time. The ordinary light oscillates. The waves of the ordinary light oscillates at infinite number of directions at right angle to the plane of the light travel. These infinite number of the directions then passing through the polarizer or Nicol prism. The infinite number directions are then converted into single plane. That single plane is called as the plane polarized light. Now, this plane polarized light is passing through a solution of sample, a solution of organic compound, let's say X. Here the X is the organic compound. Now we are going to check whether the compound X is optically active compound or not. That we have to discuss. Now a beam of plane polarized light is passing through a solution of organic compound under test. Then obviously we have two options. Here. Now what happens when this PPL, plane polarized light, is passing through an organic compound X? Then what happens? Now see. This is the original PPL, which is passing through the solution of the organic compound. Now that organic compound may rotate the plane polarized light with an angle alpha. Alpha is the optical rotation angle. This is the one possibility. At the same time, now here the compound may rotate the plane polarized light towards the another side with the angle of alpha. Again, alpha is the angle of rotation. See, here in the case 1 and case 2, these are the two cases possible when a beam of the plane polarized light is passing through the organic compound, a solution of the organic compound. In the first case, here the compound rotates the plane polarized light towards the right side. With the alpha, the compound rotates the plane polarized light towards the right side of the original plane. So that is the first case. So here If a compound rotates the plane polarized light towards the right side or clockwise to the original plane, such type of compound are called as, such type of isomer is called as dextrorotatory. Dextrorotatory. The dextrorotatory, which is represented with a sign positive, which is designated with the positive charge. And the same concept in the case 2 here. So here in the case 2, the compound may rotate the plane polarized light towards the left side of the original plane. Toward the left side of the original plane. Again, here is the alpha is the angle of rotation. Specific rotation angle. That alpha is called as the specific rotation angle. And in such cases, the isomer is called as levorotatory. Levorotatory, which is indicated with the negative sign. Which is indicated with the negative sign. Right? So, dextrorotatory and levorotatory. These two are the isomers. One isomer is, in the one isomer, the compound rotates the plane polarized light towards the right side to the right side angle. And in the case 2, the compound may rotate the plane polarized light towards the left side of the original PPL. So here these are the two isomers. The two isomers, these two optically active compounds. Why these two are optically active compounds? In the two cases, the compound rotates the plane polarized light either left side or right side. Either left side or right side. So obviously these two are called as the optically active compound. So then X is said to be called as the optically active compound. An optically active compound with two isomeric forms with opposite in rotation are called as the optical isomers. Optical isomers, and the phenomenon is called as the optical isomerism. Next, one more possibility is also there. So one of the isomer is the dextrorotatory and one of the isomer is the levorotatory. The one more thing is here, what happens? Sometimes what happens, now PPL is passing through compound X. Then here the compound X rotates the plane polarized light. This is the original plane. The compound X rotates the plane polarized light towards the right side or towards the right. So in the first case, what happens here? The angle is alpha. The second case also, the angle is alpha. Right? Because in the first case, the PPL light is rotated toward the right side. Let's say alpha is equal to plus 30 degrees. In the second case, the PPL light is rotated towards the left side. In the case, alpha is minus 30 degrees. Here what happens means, in such type of case, the compound rotates the plane polarized light towards the right side as well as towards the left side. So rotation is taking place in both the opposite directions with the same magnitude of the angle. Same magnitude of the angle, 30 and 30. Here the plus indicates the right side, minus indicates the left side. So under such conditions here, what happens here? So under such conditions, now here the angle of rotation, the specific angle rotation will be cancelled out. Then this particular compound X is said to be optically inactive. Optically inactive because there is no rotation is taking place. Such type of compounds is called as the optically inactive compound, optically inactive, and that is racemic mixture. That is called as the racemic mixture. Means equimolar mixture. Equimolar mixture. Okay, 50% of the rotation towards the right side, 50% of the rotation towards the left side. So here what happens here? Same magnitude, but different in the direction of the rotation. Same magnitude. That means 30 degrees in the both case. Same magnitude, but what is the difference? Opposite in the direction. Such compounds are racemic mixture. Racemic mixture is the optically inactive compound. So here the first one is the dextrorotatory. That is possible when the light is rotated by the compound towards the right side or clockwise. The second is the levorotatory, in which the compound rotates the plane polarized towards the left side. And those two are optically active compounds. And here see, and third one is equimolar mixture of the isomers. That is, in the compound will rotate the plane polarized light in both the direction with the same magnitude, but with the opposite direction, right? So that is optically inactive. So let us take an example. Optical activity of lactic acid. Optical activity of lactic acid. So we are discussing one example how the lactic acid is showing the optical isomerism. Generally, the structure of the optical isomerism is right. So this is the lactic acid, 2-hydroxypropanoic acid. 2-hydroxypropanoic acid is the lactic acid. So here this is the chiral center or stereogenic center. Chiral center or stereogenic center. What is a chiral center? When a carbon is surrounded by 4 different types of groups, when carbon is surrounded by 4 different types of groups, such type of center and such type of center is called as the chiral center or stereogenic center. Chiral center or the stereogenic center. So now how the lactic acid, whether the lactic acid is optically active compound or not. So if the lactic acid rotates the plane polarized light either towards the right side or towards the left side, then it is obviously called as the optically active compound. How it looks? If we go through the different isomeric structure of the lactic acid, COOH, CH3, HOH. This is one of the isomer of the lactic acid. Here see, in respect to the OH group, here the rotation is taking place towards the right side or clockwise direction. Right side or clockwise direction. Once it is the PPL, the plane polarizer, it rotates towards the right side or in the clockwise direction, and that is called as the dextrorotatory. The dextrorotatory is indicated with the positive sign, and the name of the compound is lactic acid. Lactic acid. This is the one of the possibility if compound rotates the PPL towards the right. In the second case here, the same will be explained in respect to the OH group. OH group. So with respect to the OH group, now here the plane rotates, means compound rotates the plane polarized light towards the left side or in counterclockwise, anti-clockwise. Then, so that is indicated with the L because the laboratory, if a compound rotates the plane polarized light in the left side direction, counterclock. And the negative sign is used to indicate the laboratory and the lactic acid. So these two are the isomers, D and L isomers of the lactic acid. Along that, and we have one more possibility is plus or minus. Plus or minus or DL means rotation. Compound rotates the plane polarized towards the left side and compound rotates the plane polarized towards the right side. So therefore that is generally called as a mixtures. So obviously what happens? So cancellation of the angle of rotation takes place. Obviously it indicates that there is no rotation. Alpha is equal to 0 degrees centigrade. Alpha is equal to 0 degrees. There is no rotation taking place. If there is no rotation, optically inactive. Equimolar mixture. Equimolar mixture of two isomers. So that is generally called as the racemic mixture. Racemic mixture is optically inactive. Racemic mixture is optically inactive. Now we just will discuss between the first D and L. D and L isomers of the lactic acid are called as the enantiomer. What are the enantiomer? The enantiomers are the isomers in which the mirror image of one compound over the other and non-superimposable. If you see this lactic acid in the mirror, obviously that looks like this, like our hands. If you keep your left hand in front of the mirror, it will looks like as a right hand, right? So in the same manner, if you place the mirror in between, obviously this compound is looks like this and this compound is looks like this. Such compounds are called as the enantiomers, and enantiomers are optically active. Enantiomers are optically inactive. So we already discussed that the racemic mixture is optically inactive. This is the optical activity of the lactic acid. One more example. Tartaric acid. Optical activity of tartaric acid. Right? Optical activity of tartaric acid. First I will try to write the structure of the tartaric acid. It is a dicarboxylic acid. It contains two carboxylic functional groups. Now see here, I am putting some star marks at this carbon and star marks at this carbon. These two star marks indicates what's that is stereogenic center. Stereogenic center. What is the stereogenic center? Just now I explained that when a carbon is surrounded by four different groups. If coming to the first carbon, see here, this is the first group, this is the second group, this is the third group, and the rest of the whole is the fourth group, the four different groups. Therefore, this carbon is stereogenic center or chiral center. Coming to the bottom one, this will be given the first one, second, third. Now the above part is the fourth one. So this carbon is also surrounded by the four different groups. Therefore, the below carbon, the bottom carbon is also a stereogenic center. So here, chiral center are the stereogenic centers. How many chiral centers are present here? That is indicated with the N. So here N is equal to 2. N is equal to 2. Where what is N? Number of stereoisomers. Number of stereoisomers. The number of stereoisomers can be number of chiral centers. Number of chiral centers. If you know the number of the chiral center, it is easy to determine the number of possible stereo isomers. Number of possible stereoisomers that can be given by the equation like 2 to the power of n, where n is the number of chiral center. We have 2, n value is equal to 2, 2 square is equal to 4. So here for the tartaric acid, the possible number of stereoisomers are 4 because it is containing 2 stereogenic centers or 2 chiral centers. Now we need to discuss what are the 4 possible. What are the 4 possible optical isomers, the isomers of the tartaric acid. So coming to the first one, this is the COOH group, HO in the first carbon, HOH in the second carbon. Now we concern this OH group with respect to this OH group. Now the compound, this tartaric acid rotates the plane polarized light towards the right side. Therefore, I will give the D. The sign given is the positive sign, tartaric acid. In the same manner, I will write one more structure here. COOH, HOH, HOH, COOH. So now here with respect to this OH group, this compound rotates the plane polarized towards the left side. Therefore, that is L, the sign indicated with the negative, tartaric acid. So D tartaric acid, right side rotation or the clockwise rotation. L tartaric acid, left side rotation or negative side rotation, anti-clockwise rotation. Now see here, these two compounds are optically active. These two compounds are optically active, and these two are mirror images over each other. Over non-superimposable. So optically active compounds, and these are enantiomers. And coming to the third one, because we have to see 4 isomers, right? Coming to the third one, COOH, HOH, COOH. Right? This is the fourth one. So this is a meso compound. This is called as mesotartaric acid. What is a mesotartaric acid? I will explain. Now here it is optically inactive. Why it is optically inactive? Even though it is also containing the 2 stereogenic center like other 2 isomers, because all are having the same chemical formula, but arrangement is the difference. Now first we will discuss why it is optically inactive. It is optically inactive due to the presence of the plane of symmetry. What is the plane of symmetry? If you divide any object into 2 equal halves, here, the above one is the first part and below one is the second part. So I divided equally this compound into 2 halves, 1 and 2. And first half is completely mirror image towards the second half. First half is completely mirror image towards the second half. So therefore it indicates that plane of symmetry is present. Presence of plane of symmetry. If a compound which possesses plane of symmetry, that compound is said to be optically inactive. So I can say that this tartaric acid, this isomer of the tartaric acid is optically inactive due to the presence of plane of symmetry. The plane of symmetry is indicated with the sigma, right? Now That's fine. That is optically inactive due to the presence of the plane of symmetry. Now, why it is the meso-tartaric? What is the meaning of the meso compound? What is a meso compound? The meso compound is that which is optically inactive even though it contains the chiral center or the stereogenic center. The compound with stereogenic center but optically inactive, those type of compounds are called as the meso compound. Meso compound. What is a meso compound? Compound with chiral center, chiral or stereogenic center, but optically inactive. Such type of compounds are called as the meso compounds. And coming to we have completed 1, 2, 3. The fourth one is well known, that is plus minus or DL. So that is racemic mixture. Racemic mixture is optically inactive. So here the tartaric acid, the possible number of the stereoisomer for the tartaric acid is 4 when we are discussing about the optical isomerism. The first one is the D-tartaric acid, in which the compound rotates the plane polarizer towards the right side. The second one is the L-tartaric acid, in which the compound rotates the plane polarizer towards the left side. The first and second compounds are optically active as they are rotate the plane polarized light, and these are mirror image over each other. Therefore, these are enantiomers. Coming to the third one is optically inactive compound, and it is also called as the meso compound. So, why it is optically inactive means because it presents the plane of symmetry. So, what is the plane of symmetry means? If you divided a compound, any object into two equal halves, one equal half is mirror image to the other. So, then it is said to be presence of the plane of symmetry. If a compound with the plane of symmetry is optically inactive. What are meso compounds? The meso compounds are the compounds which are optically inactive with at least one stereo center. Those are called as the meso compound. And finally, fourth one is the racemic mixture, which is optically inactive. So these are the 4 possible isomers, and this is the optical isomerism exists by the tartaric acid. So that's it. So this is about the optical isomerism. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.